Okay, our next speaker and the final speaker of the session is Ruben Cartewals, and he's also a PhD student in his final year within calculus. What a surprise. And yeah, he will talk to us about his latest paper.
Okay, hi everyone. This works? Okay, but this not. I'll go a bit like this. Okay, I'll present a paper that we wrote with my colleague Wolf. That's called Explicitly Representing Syntax Improves Sentence to Layout Prediction of Unexpected Situations. So we'll go over the parts of the title to make it a bit more clear. With explicitly representing syntax, we mean instead of using a sentence like a sequence of words, as is most commonly done in language models now, we use some kind of explicit grammatical structure, like a constituency tree, as you can see on the right. Improves sentence to layout prediction means that we take an input sentence, we feed it to a model, and we predict like a set of bounding boxes indicating the spatial arrangement of objects mentioned in the sentence. And of unexpected situations specifically means that we take sentences and corresponding sets of bounding boxes that consist of combinations of objects that are unexpected, like to have been seen together in the training data, or perhaps that have like an unexpected relation, not necessarily being two unexpected objects. So yeah, that's the title. You can find the article on arXiv, and it will be published soon in the TACL journal. So why is this relevant? I think in general, still currently, neural networks rely excessively on correlations in training data. I think this still goes for any type of neural network currently, or a lot of different types, not only language models. So they lack a compositional understanding of the underlying world or problem, meaning that when they're presented with unexpected situations or out of distribution data, they fail to like reason with the pieces that they know from before and compose them into like kind of new combinations of knowledge to handle unexpected situations. While, yeah, this is an example. If we ask Stable Diffusion to generate a horse on top of a man, it fails. It might not have been the most recent version of Stable Diffusion, but it's just an example. While for us, we have no problem at all picturing a horse on top of a man, of course. So the hypothesis is that language representations that better encode syntactical structure in sentences might lead to increased compositionality, which would enable to reason with the pieces of this like compositional structure and infer new knowledge from making new compositions, and with that being more robust to unexpected situations. And specifically here, we test whether this is the case for a visual downstream task or a kind of visual downstream task, not just for natural language understanding tasks, because there's other works that have already proven similar points, but for language-specific tasks. Yeah, so another reason why this is relevant is slightly more specific, but it's related. It's just that there are works showing that you can actually use layouts to make more robust image predictions with these kind of Stable Diffusion-based models. For example, as we see here, there's like, it's just one of these works. There are several, but which you feed like a sentence and the bounding boxes, and then you manage to actually generate a horse on top of a man, kind of. It uses the perspective, but still. Yeah. So an overview of what we did is we started by collecting an evaluation set called US COCO, unexpected situations COCO, consisting of unexpected caption layout pairs. So we asked Amazon Mechanical Turk annotators to provide links between sentence parts and bounding boxes that are both provided in the usual COCO data set. And then we used those links to replace those boxes and sentence parts with like a different category. Yeah. Then we built and trained and evaluated caption to layout models, because there existed some, but they were quite outdated. So those models take the input text, they encode it with a frozen text encoder in our case, and predict from the text embeddings with a layout encoder and a layout decoder like a set of bounding boxes. And bounding boxes just like an object label and a tuple of positions. And we can do that autoregressively, predicting bounding box by bounding box, each conditioned on the previous one, or in parallel with one forward pass in the decoder. Then we compared like this setup, let's say, using text encoders with implicit syntax or explicit syntax. I'll explain what specifically that means after this. And then we also tested and proposed an extra loss that additionally enforces the syntax structure on the outputs. So what does it mean in our case, at least for models to have implicit or explicit syntax? So we use frozen text encoders to enable a clean comparison of models that have been trained for next token prediction, like GPT-2 or 3 style. So that's the usual implicit case where the model is just trained to predict the next word. And there have been a number of works that show in various ways that these models have like an implicit understanding of syntax. Implicit meaning it's encoded in their weights in a not necessarily interpretable way, but you can do tests to see, like probes, to see if you can predict the structure from the weights, and this works kind of so. We use a number of different models like GPT-2 or in different sizes, also a version of GPT-2 trained on a smaller data set. We also tested the Llama model, like a more recent, larger language model. That's the implicit category. Next to that, there's the models that we use with explicit syntax. And with this, we mean that we take the constituency tree, we make like a linearized version of it, which is just a sequential representation of the syntax tree using brackets and constituent tags as seen in the slide. And these models have also been trained by next token prediction, so very similar, but now additionally predicting the brackets or the parentheses and the constituent tags. And some of the models use like an attention mask in their encoding transformers that like constrains the attention to only take place, for example, within the same constituent or for some tokens across constituents, and so it's to encode that structure. We use constituency trees because they're a recursive structure, and we believe that this matches some recursive structure that we can see in the visual world. There's also a number of more philosophically inspired works on that. Then we use these text models to predict layouts as you can see on the slide. So we have the text, a frozen text encoder producing a number of text embeddings, and then the layout predictor produces a number of bounding box embeddings, one per bounding box, and it does so in parallel or autoregressive. That's kind of expected. So one embedding per bounding box. Then for the explicit syntax models, we take the tree, we convert it to its linearized version, and we do the same thing, basically, using as a frozen text encoder one of the other models that I just explained. And now the text embeddings include embeddings for like structural tokens like parentheses and constituent tags. And then with the with the additional loss that we proposed, we add an additional path to the figure, where we take the structure of the sentence, not the words, but just the structure, and we encode it using like a scheme to encode 3 positions into embeddings. So you encode kind of the path. For every node in the tree, you encode the path starting from the root node to go to that specific node, taking left or right decisions. So you end up with another bunch of embeddings encoding the tree structure that we enforce on the output bounding box embeddings with a contrastive loss. And this works a little bit like this. It's like an overview. So we take the 3 position embeddings like you see on the left, and on the right the bounding box embeddings that have been outputted by the model, and then we compute, like we do an attention between the 2 of them, and then we take like the similarities as like all pairwise similarities, we sum them, and then we try to maximize the similarity between the trees and bounding boxes coming from the same sample in the batch and minimize the same thing for other samples in the batch. So yeah, that was that. Then we did some experiments that we'll go over the results of for now. So we trained all the models on the COCO pairs of caption and bounding boxes, like the in-domain ones. And we evaluated the resulting models on the unexpected evaluation set and on the in-domain test set to see if there's differences. And we evaluate models using like an F1 on just the object labels to see if they manage to predict all objects mentioned in the sentence regardless of their position. And then we use a new metric that also takes into account their like relative pairwise differences in their position to be kind of less strict than using the overlap. Because if you use overlap, like IOU overlap as with object detection, you might predict like a mirrored version, which would be wrong using overlap, but we want to count that as correct. So the results that we saw were, well, I'll summarize some of them. The first thing is that it's actually much harder to predict the unexpected situations, as we kind of suspected. There's a large drop in scores. It's like between 10 and 50% is a wide range, but the conclusion is there's a large drop. Models that were trained on more pre-training data, like text encoders in this case, like for the layout prediction, they've all been trained on the same amount of data. But the text encoders, some of them were pre-trained on much more data, like Llama or GPT-2 versus the GPT-2 model that we trained on the smaller data set. The additional pre-training data gives an advantage on the in-domain test set, but not on the unexpected situations, which means that something is going wrong. Like it doesn't help to see more correlations of known things, kind of to better predict unexpected things. Without the additional loss, models with implicit or explicit syntax perform similarly to each other on both test sets. So that's unfortunate, but it means that without the additional loss, even the models with explicit syntax, the output representations don't like retain any of the structure, or for another reason, it doesn't work better. But with the loss, that kind of provides an incentive for the embeddings to retain the structure that's found in the input. The in-domain performance stays similar, and the performance on unexpected data improves significantly for models using explicit syntax, but it drops for models using implicit syntax. Yes, So that's kind of the last point is what this figure shows. It shows the recall on the replaced objects, which is kind of a proxy for the unexpected object. With increasing weights of the loss, of the structural loss function on the unexpected test set for an implicit model, which is GPT-2, or an explicit model, which is DG, which stands for transformer grammars. And we can see that for the implicit model, it drops significantly with increasing loss weight, and for the explicit model, it increases a bit first and then kind of levels. So yeah, that's the point we make here. There are some examples of generated layouts. For the first column is an implicit model. The second column is an explicit model trained with the additional loss. And the third column is the ground truth in the evaluation set. The first two rows are examples where annotators in a human evaluation experiment chose the explicit model, and the last row is an example where they chose the implicit model. So you can see in the second row, the explicit model generates a refrigerator with a tennis racket, which is what we want, but the implicit model generates a bottle because there's like a clear correlation between a fridge and a bottle in the training data, but not between a fridge and a tennis racket. Yeah. And like the overall results of the human evaluation experiment kind of confirmed the conclusions that I mentioned before. So yeah. We used the layouts to generate images. That's not really our own work, it's just as examples. We just generated the layouts, but then I used another existing work that changes like a diffusion model for image generation to take bounding boxes into account. For the explicit syntax model, it generates, for a sheep watches people kite surfing at the beach, a number of persons with a kite and a sheep, which taking into account the boxes and generating pixels gives like an image of a sheep as we want. The implicit model on the bottom row doesn't manage to predict the bounding box for a sheep, so it fails. And if you just ask stable diffusion without any layout, it doesn't really. There's like two small dots that might be sheep, but it's not really clear. So it works better with bounding boxes. There's a similar example. I kind of picked the examples to be good ones. There are also examples where all models are bad or where they are equal, but yeah, I just picked some nice ones. Where the explicit syntax model manages to generate a cup with a phone. Yeah. I gave this presentation last week for our colleagues, and then there was someone that mentioned that DALL-E 3, which is like now integrated in the last GPT-4, or ChatGPT using GPT-4, actually manages to generate these images as well. I don't know how they do it, because behind the surface they might be using bounding boxes or different techniques. Yeah, but it's true, I tried, and DALL-E 3 manages to actually also generate nice images with most unexpected combinations of objects. But I tried a bit, and I was able to find some that it doesn't really do. At least the left one, it doesn't generate the man going up the ramp on his suitcase. It's a much nicer image compared to the one that we generated, but at least ours has a man on a suitcase. And yeah, the right one is, I think, it manages to, like DALL-E 3 also works, I guess, but it does something weird with the bat. I don't know, yeah. You can judge for yourself. But anyway, even though it's clearly better at generating even unexpected combinations of objects, I think if you look a lot, you will still find some examples where they might be useful, having the bounding boxes. Yeah, so that was it. Yeah, if you have questions. Okay.
If there are many different algorithms,
Yeah.
which could have a huge effect because.
Yeah, I can imagine. But in the end, you're going to need brackets or parentheses, kind of, or.
You could go breadth first, or you could go depth first.
Yeah, that's true. Yeah.
Up and down
Yeah.
through the tree.
Yes. Ah, yeah, that's interesting. We haven't really, because we used the kind of structural models of some existing works to, yeah, like to build incrementally on those and to be comparable to them. Also to be able to use their pre-trained models and stuff. So yeah, we kind of used their way of linearizing the parse tree, but it's true it would be interesting to see if there's other ways to do that that work better maybe. Do you have an intuition for which way of linearizing it might work best for like a visual task?
No, I don't know exactly about the visual task, but I think if you go depth first, you still have the linear order of the words is still the same.
Yeah, yeah.
If you go breadth first, you first have all the constituents, and then
Yeah.
you have the words only later, and so that might be very different on how
Yeah.
the transformer actually does.
Yeah. True. Okay, that's interesting. Thanks. Yes.
Did you use gold parse trees or automatically generated?
Yeah, like we generated them with another model, so they're not gold, but this other model gets like a really high accuracy on I don't know, like Wall Street Journal sentences or something like that, and the COCO sentences are much simpler, so we kind of assumed that they would be correct enough, but it's silver trees. So it's true that's to use the explicit models, you need trees, so that might be a drawback, because if you don't have trees and you cannot get them, yeah.
Yeah, but if you use gold trees, then you're giving your model more information than the text. So using silver trees
Yeah.
is actually better as,
Yeah.
as an
Yeah.
experiment.
Yeah, it's also more information, of course. That like information added by the other model that you use, like to predict the silver trees. But yeah,
It's
I agree.
information that a language
Yeah.
model presumably already has.
Yeah, maybe. Yeah, that's true.
Could you just kind of sort of, in terms of the errors of this model, how often does it get the layout wrong versus how often does it generate the image that is not faithful to the layout?
So we actually for the paper we didn't generate images. Yeah, I did now as an illustration, but because the paper was already long, and but so I'm not very sure if I understand your question correct. But we could, for example, check how often it predicts the right objects or like all of the objects, but not the positions. And this happens quite often. Like the F1 without positions is much higher than the F1 with positions. But I'm not sure if that's exactly what you wanted to ask.
I was just looking at the last bits that you were showing, so I was thinking there's maybe a generative model that you condition on the layout.
Yeah. This something I just found on the internet and used for it.
So now you use syntactic trees. Do you think there are other kind of structures, tree structure or other linguistic information that can be useful? For example, you showed an example of people riding ovens. And
Yes.
it surprised me that there was one bounding box for one oven, even though it
Yeah.
clearly says ovens.
Yeah.
Plural. Do you think there's more linguistic stuff we can do here?
Yeah. Probably. It's true, and this is something that often goes wrong, like the number or the like the number of objects, or plural, singular, and I don't really know why. Yeah. I think for using this type of method, you need some kind of structure, like a graph or a tree or So you could think about using different kind of structures to represent grammar in language, but like I'm not sure if that would solve the counting problem. Maybe you could use, infuse other information. Yeah, it would be interesting. Maybe like we noticed that because the COCO captions and the bounding boxes, they're not actually generated as part of one or as one data set. It's like the captions are generated for like just for captioning data sets, asking annotators to provide a caption for an image. And separate from that, different annotators provided boxes for the images, not being shown the captions that like, so they don't always align. So sometimes a caption might mention something else than the bounding boxes. Sometimes there's a lot of bounding boxes which are not mentioned in the caption at all, or this kind of effect. So this might also create like a misalignment of the, because we actually predict one from the other. So yeah, that's a bit tricky. And we try to clean the bounding boxes, like remove really small ones, or but it's also possible that this creates this kind of effect where they're not always aligned. Thank you for the questions.
Yeah, thank you, Ruben, for the talk.